Okay, so today we'll talk about voltaic cell, what are the parts of voltaic cell, what is the principle of how they work, and how can we label the parts of the cell, and how can we move from writing into drawing, and how can we match, and then lastly, how can we calculate the voltage of the voltaic cell. So when we are talking about voltaic cells, some textbooks or some people call them galvanic cells, but they are the same. What voltaic cells are equipment that produce electricity, as a result of chemical reaction. And what reaction is it? Is nothing but oxidation and reduction reactions. So they're specifically oxidation and reduction reaction. So see what are the parts of, pretty much the parts of the voltaic cell. So let's suppose that we have two beakers, which one is filled with zinc sulfate solution, and the other one is filled with, let's say, copper sulfate solution. And what do we do here? We put a plate of zinc into the zinc sulfate and a plate of copper into the copper sulfate. And as soon as we connect those two with a wire, what do we notice is the motion of the electrons. And when the electrons are moving, then electricity is produced. You can see and prove this with a very simple voltaic cell like this design here, by placing a bulb there or an ampermeter where you measure the intensity of the current. Another important part of the voltaic cell is the salt bridge, but we will talk about this, what is important and why do we need to have a salt bridge into a voltaic cell, almost at the end of the video. Not almost, yeah, but somehow later on in the video. Okay, so now let's take a look closer to each of those solutions. So when we have a zinc sulfate in a solution, that means that we have zinc ions. So in this part of the on this beaker, what do we have with that metal plate? We have zinc metals here at the plate, and we have zinc 2+ along with SO4 2-, but we are not bothering to write it now because it is not quite important as per now. Okay, so this is what is it on the zinc solution and with a plate. And then on the other one, on the copper solution, what we have, a copper sulfate solution, what we have is we have the copper atoms and we have copper ions from the zinc copper sulfate. Because when we have solution, then copper and sulfate being an ionic solution compound will be dissociated into ions. Great. And now when we connect those two, what is happening is that they are having competition as to which one will grab electrons, which one is stronger to grab electrons. So what is happening is that copper 2 is saying, give me the electrons to zinc metal. And then since copper 2, even in your data booklet on page 7, has a higher electric potential energy or stronger, it's a stronger oxidation agent, has a higher power to grab the electrons in comparison to zinc. So the zinc 2 plus and copper 2 plus are having a war, let's say so, and then they are saying that which one is the strongest one to grab the electrons. And it ends up that you can prove that even from the data booklet, as I said, that copper 2 plus is stronger on attracting electrons from zinc metal. So what is happening in this case, copper 2 plus is saying, okay, you have to give me electrons to zinc metal, so to zinc atoms. So this zinc is saying, okay, I will give you 2 electrons. So it's giving 2 electrons. And by giving 2 electrons, this zinc now is converted into zinc 2 plus. And the electrons are flowing into the wire and going to copper 2 plus. And as copper 2 plus is absorbing those, is taking those electrons, is converted into a copper atom. Okay? And this is the process that is happening, so that when the electrons flow into the wire, what it is that the electricity is produced. And now, since zinc atom here was turned into a zinc ion, then and copper 2 plus is turned into copper metal, what do we see is that since metal ions usually are dissolved in water, we see that this zinc plate is kind of dissolved. It's becoming less and less, while copper is building up into the plate. And in this case, what we will notice to the zinc plate is that is becoming smaller and smaller, while the copper is becoming bigger and bigger. So they will change the shape and the mass, of course, because this is dissolving, continuously releasing electrons to the wire, because copper 2 is pulling the electrons and has a stronger pull, and then copper 2 is building up as the metal. So now zinc atom, by giving those electrons and becoming a zinc ion, it is losing electrons. Okay, so from zinc, it is losing electrons to become zinc 2 plus. Okay, plus 2 electrons. So that means that on this side, on this beaker here, what is happening is oxidation. And then when we take a look at the other beaker, in which copper ion is grabbing 2 electrons to become a copper solid, what is happening here is actually reduction. Reduction. I was having a brain fart. So, in other words, and we mentioned this a bit even on the first introduction lesson of the thermochemistry, we give those a specific name. So anode is related to oxidation, so we call this plate as the anode and this plate as a cathode. So now, how do you remember this? One way to remember is red, so cathode red, and anox. So anox is, anode is where the oxidation is happening, and cathode is where the reduction is happening. And very often we call this as the oxidation half cell, and this as a reduction half cell. Okay. So oxidation is anode, and usually this part of the cell is called as the oxidation half cell, and reduction is cathode, and it is this part of the cell is called reduction half cell. Okay, so now if we summarize, what do we have as the oxidation in this cell, or what is in anode is the same thing, is zinc solid is giving 2 electrons to become a zinc ion. And what is happening in the reduction or cathode is copper 2 plus in aqueous solution is receiving those 2 electrons and is becoming a copper solid. However, it is very important to know that how to draw or how to represent a voltaic cell in the cell notation. Well, cell notation is nothing but a shorthand abbreviation of the chemical reaction in the voltaic cell. So it's pretty much telling what is happening without being able or drawing the cell as we draw here in this lesson. So let's see now what is happening, or how do we represent a voltaic cell without tell what is happening in the voltaic cell without actually drawing what is happening, drawing the cell itself. So we always start with from the left, and we start with the oxidation half cell, and then we move to the reduction. So on the oxidation, here we have it. On the oxidation, on the anode, what is happening? We start with zinc. So zinc solid, and then we have a line, because this is within the cell, the half cell, actually, in the half cell. It is becoming, so see here, it's becoming, it's giving those 2 electrons, and it is becoming a zinc 2 plus aqueous solution. And then we draw two lines to show that this is what is happening in anode. Okay, now we'll start with cathode. And what is happening in cathode, we start with Cu2 plus, actually this is 2 plus, Cu2 plus, in aqueous solution, and then we'll end up, as you see here, by grabbing those two electrons, we'll end up into copper solid. And on this way, what we are saying is that this is happening in anode. This one here is happening in cathode. This is the oxidation, and this is a reduction. Okay? So now let's talk a bit about what is the purpose of the salt bridge. I will stop the video now, draw the voltaic cell again, and then you will see it with the salt bridge and what is happening with it. So now we know that we have here on this half cell on the anode, we have zinc 2 plus, and what we have here as a build up into the cathode, we have copper built into the cathode. So this, the anode is wearing up because of the oxidation, and in the cathode is building. If we are leaving it like this, what will happen is that we will end up not having anything into the anode to produce electrons to go to the cathode. Okay, so this is anode and cathode. So if we leave it like this without the salt bridge, then what happens is that the zinc plate will be wearing up, and then we will not have any more electrons to provide for the flow between zinc plate and copper plate. Okay, so to do this, what we built into the voltaic cell is that salt bridge. This one here is salt bridge. Now, what salt bridge is a solution of sodium chloride, which is the table salt. So that means that we have two ions here. We have a sodium ion, Na+1, and we have chloride ion. Okay, so what will happen now is those will go and move to where they are needed. Move where they are needed. But where are they needed? So where is a positive charge needed? It is needed in the cathode, because what is happening in the cathode, we don't have too much C2 plus, because C2 plus is built up here, and it is becoming a Cu2 plus. Sorry, it's becoming a Cu metal. So what is happening in the cathode is that Cu2 plus 2 electrons is becoming solid. So the charge, the positive charges here are missing, and what we have here is SO4 2 minus, a lot of SO4 2 minus. So then those sodium are moving toward the cathode. Okay? And then on the other hand, what we have in anode is that we have a lot of zinc plus, because what happened in anode, what happened is the oxidation. So what we have is a zinc solid plus 2 electrons is becoming, sorry, zinc solid is giving 2 electrons, and it's becoming 2 zinc 2 plus. So chlorine or chloride ion will be moving toward the anode. So this is why the anions are moving to the anode and cations are moving to the cathode. Okay? Okay, so this is the principle of a voltaic cell and the parts and how do we write a voltaic cell, starting with anode, what is happening in the anode, and then moving to cathode, and what is ending up into the cathode, and all the parts and why are they, and what is the motion. We'll do the other video where we will talk more about voltaic cells.